We saw in the standard Bertrand model, where products were homogeneous, that firms priced at marginal cost in equilibrium. We saw in the shopping cost model that when we introduced product differentiation in the form of differing locations, prices could be above marginal cost. Here, we're going to look at something called the hoteling model of product differentiation. This is a model of horizontal differentiation. The difference between the hoteling model and the model in the shopping cost game is that locations are represented by a line, and the different products are arrayed along the line, and therefore we can use this model to consider product positioning. The firms choose where they locate along a line. So let's think of a differentiated product, breakfast cereal, and let's suppose that breakfast cereal is differentiated along just one dimension, and that dimension is sweetness. So consumers have different ideal levels of sweetness, and we can see in the cartoon that Calvin really likes sweet cereal, whereas Hobbes prefers a less sweet cereal. In the diagram here, I have a line from 0 to 1, and at one end I have rolled oats. That's a very unsweet cereal. And then at 1 I have chocolate frosted sugar bombs, which is a very, very sweet cereal. So we have sweetness ranging from 0 to 1 along the line. We can represent products as points along the line, and we can also represent consumers' ideal sweetness as a point along the line. So Calvin likes very sweet cereals. Let's suppose Calvin's ideal variety is a sweetness of 1, whereas Hobbes is somewhere over here. He likes a less sweet cereal. Now here I've used the line to represent the degree of sweetness. We can also think of the line as a street, and different locations along the line are different physical locations. So one shop could be located at 0, another shop located at 1, and consumers are located at points between 0 and 1. So this hoteling line can represent either a physical differentiation in terms of location, or differentiation in terms of things like sweetness, crunch, and so on. So sometimes it will be helpful to think of this as a street in order to understand the model. In the model, we'll assume there are two firms, A and B, and they're located at LA and LB. So if LA and LB are different, we have a differentiated good. LA and LB are just numbers between 0 and 1. Each firm has a constant marginal cost, and for the diagrams we'll assume that that marginal cost is 0. The firms set the prices PA and PB simultaneously, and each firm's goal is to maximize their profit. So the only difference here to the Bertrand model is that we have differentiation. The consumers, well, there is a continuum of consumers with a total number of consumers of 1, and they are distributed uniformly along the line. So this means they're spread out equally along the line. Half of the consumers are to the right of the halfway point, and half of the consumers are to the left. 3/4 of consumers are to the left of 3/4, and 1/4 are to the right of 3/4. So they're spread evenly. A consumer's location represents their ideal variety. So consumers are willing to pay V for their ideal variety. And then if they consume a good that is not their ideal variety, they pay a travel cost, or they incur a disutility of T for each unit of distance the variety deviates from their ideal variety. So the willingness to pay for a variety is V minus the transport cost T times the distance they have to travel away from their ideal variety. In the non-geographical interpretation, a greater T means that consumers care more about deviations from their ideal variety. So this is how we capture the product differentiation for the consumers in their preferences. Each consumer's goal is to maximize surplus. So in order to find the equilibrium of the game, we first need to find the demand functions of each firm. So to begin with, let's suppose that A is located at 0 and B is located at 1. So if A is located at 0, then LA is 0, and LB is 1, because B is at 1. Now let's consider a consumer at position X. In order to buy from A, they will have to travel a distance X. And in order to buy from B, this consumer will have to travel a distance 1 minus X. So this consumer will incur a travel cost of T times X to go to A, and therefore is willing to pay V minus TX for A's good. Whereas to buy from B, they will incur a travel cost of T times 1 minus X, and therefore is willing to pay V minus T times 1 minus X for B's good. So a consumer will prefer to buy from A as long as this number here, minus A's price, is larger than this number here, minus B's price. So here we have the consumer surplus from a consumer at X for good A, and the consumer surplus for good B. Now we can cancel the V's here, and we can rearrange, and we end up with PA plus TX less than PB plus T times 1 minus X. So this inequality says a consumer will prefer to purchase from A as long as the delivered cost for A is less than the delivered cost for B. So a consumer will prefer to buy from A if, once we take into account the transport costs, the cost of buying from A is less than the cost of buying from B. In the next 3 diagrams, we're going to derive the demand curve for firm A given that firm B's price is PB dash. Now in the first diagram, I'll find the demand for A for just one price of A, the price PA dash. So on the left-hand vertical axis, we are measuring A's price. In the right-hand vertical axis, we're measuring B's price. And on the horizontal axis, we have the hoteling line. Because we have this uniform distribution of consumers, we can also think of this as measuring the quantity demanded for A from 0 to the right, and the quantity demanded for B from here to the left. We are always going to assume that the consumer buys either from A or from B, so their demands sum to 1. So at these prices, PA dash and PB dash, we can work out what is the delivered cost for each consumer. So in this line here, I have the delivered cost for a consumer buying from A. If the consumer has X equals 0, so they're positioned at 0, then the delivered cost is just the price PA dash. Whereas if they live further away, they also incur the transport cost T times X, and this just gives us a straight line of slope T. Similarly, the delivered cost for B is a straight line from PB dash with an absolute slope of T. And consumers will buy from the firm with the lower delivered cost. The delivered costs are the same where the 2 delivered cost lines intersect, which is at this point here. So the consumer with the same delivered cost for both goods is X dash. This is the indifferent consumer. This consumer's delivered cost at A is the same as their delivered cost at B. The demand for A will be everything to the left of X dash, because anyone to the left of X dash, the indifferent consumer, will have a lower delivered cost from A than from B. Anyone to the right will have a higher delivered cost. So this distance is the demand of firm A when its price is PA dash and the other firm's price is PB dash. The rest of the consumers go to firm B. So we found one point on A's demand curve. This point here is on A's demand curve when B's price is PB dash. It's the point on A's demand curve when A's price is PA dash, given that firm B's price is PB dash. In the next 2 diagrams, we're going to find some other points on A's demand curve and then draw A's demand curve, given B's price is PB dash. Now in this diagram, we still have PB equal to PB dash, but now we're going to look for the price of firm A that gives it all the demand. So we're looking for the price that gives A a demand of 1. So when is A's demand going to be 1? It's going to be 1 when the delivered cost for A is less than the delivered cost for B for all of the consumers. Now the highest price where that happens is going to be where the consumer located at 1 is just indifferent between buying from A and from B. That is when the delivered cost from A and the delivered cost from B are the same. So we're looking for the delivered cost line for A that goes through this point here. So we're going to draw a line of slope t from this point over to 0. And the price we find on this axis, the intercept, will be the price where the consumer located at 1 is just indifferent between buying from A and from B. So PA double dash is the price that gives firm A a demand of 1. The delivered cost line here is PA double dash plus TX, and it just intersects B's delivered cost line at this point here. So a consumer located at 1 is just indifferent between buying from A and B. So A's demand is 1. So we found another point on A's demand curve. When its price is PA double dash, A's demand here is 1. So far we have 2 points, this point and this point. The next point we're going to find is the point on the vertical axis here, where firm A's demand is 0. So now we're looking for the price where a consumer located at 0 is just indifferent between buying from firm A and from firm B. So when is that the case? Well, it's when firm A's price is equal to this price here, which we will call PA triple dash. So at this price, A's delivered cost line is everywhere above B's delivered cost line. So this is a third point on A's demand curve. The indifferent consumer in this case is located at 0. So we found 3 points on A's demand curve. We're now going to join them up with a straight line. The reason we have a straight line demand curve is because we have this uniform distribution of consumers. As we move to the right, we increase the quantity demand at a constant rate. So let's draw a line through those 3 points. So this is A's demand curve when the price of firm B is PB dash. So we found A's demand curve. It's different to the demand curve we saw in the Bertrand model. This one is a smooth downward sloping demand curve like we're used to. We don't have this discontinuity in demand, and so there's going to be less incentive to undercut each other because a small decrease in price now only gives a small increase in quantity demanded. Now, what would be A's best response to B's price of PB dash? Well, to find that, we just draw the marginal revenue curve of firm A. So we just do what we do if A were a monopolist. We look at A's demand curve, we find the marginal revenue, which is twice the slope of the demand curve and has the same vertical intercept. So this is firm A's marginal revenue curve when B's price is PB dash. The marginal cost here we assumed was 0, so we're looking for the intersection between the marginal revenue curve of firm A and the horizontal axis. So the optimal quantity is here, the optimal price we find off the demand curve is over here. So the best response of A to B's price is this price here. Now as we vary PB dash, that's going to shift the demand curve of firm A. If PB dash goes up, then the demand curve of firm A will shift out, and the marginal revenue curve will shift out too, and therefore firm A's best response will go up. Now what does the Nash equilibrium look like? Well, the Nash equilibrium is where both firms are playing a best response, and so they must both be profit maximizing. So the prices here, PAN and PBN, are the Nash equilibrium prices. So I've drawn the delivered cost line for both firms. From that we get the demand in equilibrium, which is a half because the firms are identical and because they're located at 0 and 1. And we can see this indeed is a profit maximizing quantity and price because the marginal revenue of firm A crosses the horizontal axis here, the marginal cost, at this point. If we drew the demand curve for firm B and the marginal revenue for firm B, they would look very similar. They would be the same as these red lines, but reflected about the halfway point here. So the main thing to notice here is that the Nash equilibrium prices are above zero, they're above the marginal cost. So in the hoteling model, with a positive transport cost, the Nash equilibrium prices are above marginal cost. Each firm has some market power. So the introduction of product differentiation has changed the demand curves of the firms. There's no longer this horizontal portion at the rival's price, and therefore we don't have this strong incentive to undercut, and we end up with a Nash equilibrium where prices are above marginal cost. So what happens if we change the level of transport costs? So we can think of a change in the level of transport costs as an increase in product differentiation, given that we've fixed the locations of the two firms. Or we can just think of it as consumers care more about deviations from their ideal variety, or in the geographical interpretation of the model, be an actual increase in the cost of going from one place to another. So what effect does it have on the demand curves? So if we increase T, what is it going to do to A's demand? So to see what it does, we have to look at the effect on the delivered cost line. So let's look at this delivered cost line first. So this is delivered cost line when firm A is pricing at PA double dash, the price that was giving a demand of 1. If we increase T, then the slope of the delivered cost line will increase, and the price that guarantees A gets all the demand will actually decrease, because the consumer at 1 now has to spend more to buy from A, because the transport cost has gone up. So the new delivered cost line here is in blue. And we find that this is the price where A gets all of the demand. So we found one point on the new demand curve after this increase in transport costs. When the price is equal to this value, the demand of firm A is 1. So this is 1 point on A's new demand curve. The other point we're going to find is a point on A's demand curve where its demand is 0. So now we're looking at where the delivered cost line for B intersects this axis here. That is, when is the consumer at 0, just indifferent between buying from A and B. So B's delivered cost line has got steeper, and now the price where it intersects the vertical axis here on the left is here. So this is another point on A's demand curve. And if we draw a line between those 2 points, we get A's new demand curve after the increase in transport costs. So to summarize, an increase in T is going to make A's demand curve steeper. So an increase in transport costs gives A more monopoly power. Now its changes in price have less of an effect on its quantity demanded. In the extreme, where T goes the other way to 0, A's demand curve will get flatter and flatter, and in the end we'll end up with the same demand curve we had in the Bertrand model. And the other thing that will happen as we increase T is that because of this increase in market power, the Nash equilibrium prices are going to increase. So the Nash equilibrium prices are increasing in the transport cost T.